So this is our departmental seminar, and it's my pleasure to welcome as a speaker Professor Nick Holliman, who joined our department not that long ago. I think about a year, almost exactly a year, in January 2022. Nick actually hasn't spent in academia most of his professional life. It was more or less balanced between the industry and academia. After getting his PhD and having a couple of academic posts, then Nick decided to move to industry, spending a number of years at Sharp's labs at Oxford. Leading there on a number of projects. A couple of projects I listed here because they just caught my attention. One of them was stereoscopic 3D displays. So Nick was leading on a software development team in that line of producing of stereoscopic 3D displays. Which then went into the production, and I believe they were sold in quite some number, going into tens of millions worldwide. So that's what is called proper impact of research. And also, while doing that, that's part of this of the research was patented and then used in other contexts. For example, was used in producing movies, 3D features by Dreamswork. So if you keep watching them, there are some movies which you can just point out that yes, this is based on what I've been doing, and they're based on my research. So after that, Nick decided to move back to academia to be more free in pursuing his research. That was first Durham University, then a couple of other universities, Newcastle University just before King's, and from January 2022, Nick is at King's as a professor in informatics department, and also, maybe predominantly, I don't know which one is the main role, it's the director of CASP London, Center for Urban Science and Progress. And in addition to those two roles, Nick also tries to improve and increase the connections between our department and generally King's and the Alan Turing AI Institute. So Nick's work always was concentrated on visualization, on developing, creating new methods for visualizations, and also to evaluate them. And I believe, and as I read the abstract, that will be part of that's what you will be talking about these experiences today. Nick?
Thank you, Thomas. That's great. Yeah, it was fun being in industry. I've worked in everything from a small startup to a major multinational. And the startup is where from month to month you don't know if you're going to get paid. And the multinational is from month to month, you've got to deliver something for the big demos at the end of the year. And as Thomas was saying, we did some really large-scale selling consumer products. But to give you an idea of how long impact takes, we designed the first version of something called the Nintendo 3DS, 3D display with head tracking. Some of you may have one still. They stopped selling them last year. It was 10 years after we did the research before it went into product. And unfortunately for all the universities in the country, we weren't in universities, so they couldn't count it for ref. But the work I did on 3D movie quality control was refable and was an impact case at Durham. And those algorithms are used by Disney and DreamWorks and others. And are still used today, actually, in various ways. And they're owned by an American company called RealD, who make all the money out of them. So don't expect me to be rich. And the patent process is a really interesting one, and not really well understood in most universities, I think. But we won't go into that today. One of the themes through my whole career has been slightly different, I think, from many people in academic visualization, has been to use the science of what we know about perception and cognition to make the systems that produce images work better. So, and I'll talk through what that means in a couple of examples. But that's unusual in that many visualization researchers don't do that. I'll mention one or two who do on the way through here. We might have time to talk about CUSP at the end. Really exciting at the moment because CUSP New York, who is our CUSP mothership, has got some really large-scale initiatives happening and starting just this year. I was out there last week? No, a week before, talking to them. Okay, so why do we want to do data visualization? Why do we want to draw pictures of any kind of thing? Well, we could go to authorities like Kofi Annan, who said if you can't see it, you can't solve it. Without good data, we're flying blind. He was talking there about Africa and maps, particularly of hunger and food distribution in Africa. That was in 2018. More recently, last year, Patrick Vallance was reflecting back on the pandemic. And in fact, I was at a workshop just last week at the Newton Institute in Cambridge with a whole group of scientists who were reflecting back on the pandemic. And the civil servants were saying exactly the same as Patrick, that data visualization tools have become critical in government now. They can't push policy to ministers without giving them a visualization of the data and the meaning behind the policies. And they've found, as it says here, ministers are now pulling for visualization. And this is a bit of a change in the last few years. Previously, visualization has been quite specialist in science and technical groups, really. But there's an underpinning problem, which Robert Cassara from Tableau pointed out to us all in 2016. Is this really data visualization fit for purpose? And I think quite a lot of us think it's not. There's not enough science and engineering underpinning visualization. There's an awful lot of design studies, awful lot of just pure design that's not evidenced. And I think if you want to have a summary of what we do know about what's evidenced, Steve Franconeri's paper in 2021 is a really nice summary of that. So where I'm coming from is that we need more science. I'm advocating we need more science. We need more theoretical and empirical knowledge about what really works in visualization. We can't just go to the existing books and look at people's theories and ideas, informal theories and ideas about what works. So today, and I'm going to try and make sure I stop for questions. Oh, okay, I should go a bit quicker. I'm going to cover three things. How can we? I'll go through quite a detailed study of how we think we can produce visualizations which represent data truthfully. I'll do a little bit about human-machine teaming to validate visualization quality, and that's in the context of higher education and automated, semi-automated marking of visualization assignments with students. How do we combine AI, machine learning, machine vision to help us mark and assess student work? And then finally, I'll talk a little bit about work we've been doing over the last 10 years or so on data visualizations for decision makers. And by decision makers, I tend to mean people making critical decisions, and it's easiest to think of that, people like army commanders in the field, all needing to receive the same information and understand the same information from a visualization. How can we go about making that effective? Talk a bit about that, and its use using COVID as well. Okay, what's data visualization? Well, there's this gap, and there's more and more data in the world, more and more complex algorithms producing more and more data, and more interpretations of data. But humans, people, ourselves, we still need to access and use this data. And while there might be vast amounts of data on the right here in the cloud, it's got to be turned into something that people can see, read, view, and understand. So they need to be able to have a perceptual and cognitive framework in which they can understand that data. And I think, actually, if I have a criticism of today's AI-driven world, it's there's not enough study of this link back from machines to people. That this pipeline is constrained by people. We're not evolving fast enough to cope with the speed at which data is arriving, and concepts and ideas are arriving on the left of this picture. You might say, why use data visualization? I like Johann Heinrich Pestalozzi's quote in about 1790. Visual understanding is the essential and only true means of teaching how to judge things correctly. The learning of numbers and language must definitely be subordinated. And this, if you're a visualization research, that's great. You think, well, who is this guy from 1780? He set up schools in Switzerland and a method of teaching that was very visual, which eventually taught Einstein. And Einstein always said during his career that he had to see things before he could work out the maths and the text for them. So there was something in there. I think really visualization is going to speed up this process of going up this pyramid from data through information and knowledge to wisdom. But it'll give you faster, more accurate cognition when it works. And I'll try and convince you that some of the things we've done have done that. Through designed images has been the lifetime of visualization. Really, it's been people designing things and trying them out. Our very own Florence Nightingale became very famous with his coxcomb diagrams. They're actually very distortion-inducing. The pie chart shape actually overemphasizes their message, but still she got her message across. And I love her quote, "To affect through the eyes what we fail to convey to the public through their word-proof ears." It's very direct. 165 years ago, more recently, Otto Marie Neurath, who created this Vienna method, isotype, in the 1930s. Originally in Vienna, they moved to the UK, where they did a lot of work. There's a museum in Reading with a lot of their work there. They were pushing a more urban, actually, understanding of things. They wanted to sell the new cities in Europe. And they said, words divide and pictures unite. And they were trying to describe the changes that were happening in society at the time in a museum about Vienna and its change. These iconographic pictures on the right they came up with led to the Geneva Convention on Traffic Signs, which still controls most of the world's traffic signs today, and actually probably underpin almost all the icons and emoticons on your phones and tablets. So, how can we know that data visualizations are representing something truthfully, or at least in the way we intended? We don't have to know that the thing they're representing was true. And we can go to the excellent philosopher, now emeritus professor of philosophy at Cambridge, Baroness Honora O'Neill. She's done a lot of work for the Royal Society on open data, and she's quite critical of the open data movement, that transparency of data is far, far from enough if you want to actually use data effectively. And she came up with 3 principles, which we'll come back to in a few minutes. Data has to be accessible, so that's the open part, but it also has to be usable. There's no point having accessible data if you buy a £20,000 piece of software to use it. And it also has to be comparable across different systems. And you could imagine data coming out of, let's pick 2 things, 2 LLMs, ChatGPT and its nearest competitors. Are they even comparable? I don't. Is there any way in which you compare the trustworthiness of them? It's very unsure that they are. Although more standard mathematical modeling usually comes with error bounds, which are comparable. So transparency doesn't mean trustworthiness, and she's very driven by Kantian philosophy that you can have rights to things, but you also have to take on responsibility for describing them in a bit more than having the right, using them effectively. So here's one of the problems that we took on a few years ago now in Newcastle. We they still have, an urban data observatory there, taking about 4 million readings from across the city every day, everything to do with air quality and air pollution. And this is just one set of sensors in a small area of the city, and a set of icons that we used at the time to represent temperature, the mean temperature value of the last hour at each of those locations. I think there are about 400 sensors spread across the city centre, so it's quite densely sensed compared to London, which is very poorly sensed, certainly with public sensors at least. And we showed this back to the local council, who immediately said, okay, well, we know some of these sensors are very cheap. We know some of them are very expensive. Some cost a few £100s, some cost tens of thousands of pounds. Which ones can we rely on? So we went away to think about how we represent uncertainty information, and that's set off a long track of thoughts, which I'm going to try and summarize in the next 10 minutes or so. So you need to go back and think a bit about uncertainty and what it means. Uncertainty is a grand challenge in visualization. To most scientists, it's very natural to represent uncertainty about what they know. They'll come with error bounds and all sorts of measures, which we'll see in a second. For the public, uncertainty is still quite a negative thing, and scientists conveying uncertainty in public presentations are not normally well received. It tends to convey a sense of ambiguousness, and the whole climate change debate partly comes about because the way uncertainty has been presented has been not well thought through. However, in science, it's a positive thing, and it's good to know your uncertainty. If you can bound your errors, that's great. And it's led to this certainty bias, and you see it in public policy making, all decision makers just like, this is definitely the way we're going to go. But truth in science is not this absolute thing. In the humanities, arts and social sciences, I gave a talk at CRASH, which is the Centre for Research in Arts, Social Sciences and Humanities in Cambridge a few years ago, and started talking about uncertainties. And they had no idea what I was talking about. They had no idea about variance or standard deviation, but they fed back that their idea of uncertainty was decay of things over time. If you've got a photograph in an archive, it decays. So there's some archival uncertainty in things. Very different idea of uncertainty to the sciences. And Bruno Latour, who was, in the beginning of his career, very much associated with the anti-science movement, moved more recently to be more sciencey and pro-science. Certainly talked about uncertainty in his book On Earth, that the world's not this solid continent of facts sprinkled by a few lakes of uncertainty, but a vast ocean of uncertainties speckled by a few islands of calibrated and stabilized forms. Very few areas where we have certainty. And therefore, conveying uncertainty to people is quite important. So what's our uncertainty of our temperature measurement, going back to Newcastle? Measurements all vary naturally. This is the temperature in an hour. You can see that it was a declining hour, 1700 to 1800 hours in the night. And it was varying around the trend line. And you could measure the variance, standard deviation, or more relative measures. Coefficient of variation, index of dispersion are good measures of uncertainty too. And the thing that kind of is driving us in the project is how can we present this to people with no knowledge of this maths? It's quite easy, and it was very easy at the Newton Institute last week to sit back and a room full of mathematicians know that they knew what variance was. But 80% of the public don't have maths at GCSE, age 16. I would probably guess another 15% don't really use or understand the maths, certainly not of uncertainty. So how do we get to a point where we can engage people in a conversation around the uncertainties of things without putting them off, but at the same time being very clear about this? This question at least goes back to the 1960s. The CIA did a nice report on this, comparing numerical and written textual forms of uncertainty communication between analysts. And they decided that they would use text representations rather than numbers. Okay, so we've got this problem, we want to convey uncertainty. We've got another problem, is how to do it. There are certain standard forms in the literature. Blur is one of them in visualizations. Transparency is another one. We've tested both of those, although we've not published on that, and they're both really poor ways of conveying information consistently between people. Blur and transparency don't survive going onto different screens with different brightnesses and different contrasts. You have to have very carefully calibrated screens to know the levels of blur and transparency are being communicated correctly. So we started to think about different ways of doing that. And we came across a work on information theory and entropy from Min Chen in Oxford, who Rita and Alfie know very well. I dismissed this for years. I thought this was no point thinking about information theory because people are not information theoretic decoders of information. They don't obey the data processing inequality. If I don't send you a signal, you start making stuff up in your mind. Right? If I stop sending messages, machines won't do that, people do. So they're not information theoretic. But at some point, we decided that people could be information theoretic receivers of information if you regard them as error-prone, noisy receivers of information. And then the destination at the end could be modeled using information theory. And you could think of us as receivers of pure information in some sense. This pipeline I won't spend much time on, but this maps out in some detail how data transforms from digital form into optical form, into neural form as it goes from a machine to a person. And it's quite important to consider those stages because the display, as I was just saying, for transparency and blur will not always record and reproduce signals that you assume it is doing. It is very common for visualization people these days to assume a tablet and a phone and a display and a projector will all show the same thing, and they don't. They don't show the same colors, they don't show the same brightness levels. So there's chunks of work in this to do yet. Anyway, so going back, we think about information as a perceptual scale. If you're sensitive to information, you're sensitive to amounts of information in a signal. So let's not worry about what the information is yet. We'll come back to that later. The idea we were working with was that we could use information content itself to code value. And going back to 1987, there's a paper by Cutting and Garvin where they'd investigated the beginnings of this. They looked at how fractal dimension in a shape could be used to order it. And they did a study of ordering shape by fractal dimension. And they found that people could order shape by fractal dimension. So complexity of shape, which is an information measure of the shape, without knowing what it's representing. And another study by Wilkinson at UWA, University of Western Australia, visited their group just over Christmas, was also looking at your sensitivity to shape. So you're very, very sensitive to these tiny shape changes. And they were disturbing shape. The first one on the left, you can tell that it's not a perfect circle, even though there's the tiniest deviation from a circle. So you're sensitive to pure information content in shape. So we thought, okay, well, can we then use that to generate a set of glyphs, shapes that are ordered, and use that order to represent a value, and that value could be uncertainty or some other second value. The problem is we're fighting this against 30, 40, 50 years of some French guy called Bertin who said no one could ever do this. And even as recently as 2014, Tamara Munzner in the US, in her book on visualization, said you can't order by shape. People can't see an order in shape. So we set out to test whether that was true by using this set of shapes where the complexity, the information content, pure information content, entropy in each shape, increased by a factor of 2 at each level. And because we wanted to be very rigorous in this, we tested it globally. We didn't just test it in the UK. We ran a pilot in the UK, and then we ran, before COVID, we ran a study in Australia and a study in Switzerland in person. And then we had to switch online during COVID to keep doing it. So if you could order this, if you couldn't order this set of shapes as per Bertin and his theories, you get chance performance, which here is that 0.5 line. And you can see for each of these shapes, they're being put in the correct order when compared to all the other shapes, pretty much 80 to 90% of the time. So we've got some pretty strong evidence that you don't randomly assign these order. You can see this order based on shape. And therefore, we can start to think about using shape as a scale to represent other types of information which we're interested in. What can you compare this to? Compare this to brightness levels, if this was brightness levels in a standard visualization package. And that gives us a way to add a second variable to our city data. So we did just that, and this is the 3D map again, zoomed in a bit more. And these are now all of the temperature sensors representing an information temperature value. We're on Met Office temperature scale, which is why it's kind of strange yellowy, more mustard color on this screen, but yellow on my screen, for the temperature. And then around it, the shape is representing the uncertainty. So the more complex the shape in that case, the highest uncertainty we're assigning it. And so you will see some shapes, have I got a mouse? No. Oh yeah, like this one. This one's got very low uncertainty, very high certainty that this was varying very little over the hour. And whereas the highest one here, this is a very unreliable one. We wouldn't rely on that as representing shape over the hour. And I'll show you a couple of other examples of applications in a second. So I did a few search tasks with this type, and people could indeed find low and high values in here quite accurately. So we're reasonably happy that it worked. Moving on to one of two other applications we've tried so far to date with this. This is, if we had a touch screen, we could go and do it, but we don't. I have to try it in my office one time. This is a set of MNIST trained neural networks, which show different qualities. You can sketch a number, the system will recognize the number, it will give you the probabilities that come back from the neural network, the sum of the weights, as a little bar graph, and you'll see on the left a very high bar graph, but we're using the glyph to say this is a very sure result from this network. In the middle, similar thing, but the network's a bit less sure, and hopefully from the glyph you'll see that. And on the right, we've done something to the 3 to make it not work very well, and it's decided it's a 5, but it's very unsure about that. So hopefully the glyph's a lot quicker to read for you than the graphs at the bottom. The blue plot's a saliency plot, which we sometimes put up there as well. So we tested in that, and it kind of worked. We didn't test it formally, we just implemented it to try it out. And then we've put it into a Python library, which you can download, called Vizent, and that allows you to do these bivariate glyphs within any matplotlib plot, and there's one of them here in a map, and again, it's the same temperature sensors on a different day in the centre of Newcastle, showing each of their variances, and the temperature about a toasty 11.1 degrees centigrade, and variability now on, I think, standard deviation scale. So we've done a couple of things in trying to convey uncertainty here. We've turned it into a categorical variable, where it's a number of levels rather than a scale, a real number scale. And we've then turned that into a shape, so you can quickly pick out the shape and quickly, we hope, judge the level of confidence that you could have in the data from that particular sensor. Moving on to some work that's just gone off for review now. We've taken that and applied it to graph networks. So as well as, I'm going to say very much about this because time is quickly running out, but as well as the nodes in the network, we've done a set of experiments on edges and similar things using frequency of shape. Weirdly enough, Bertrand actually said you could order this on edges and not shapes on nodes for some reason. But anyway, we tested it, and you can order these in the same way you can order shape on the circles. And then these are so the actual application, which this isn't, was Facebook's global data center network, and the transmission, the bandwidth of traffic going across each link, and the variability of that traffic, as well as at nodes, the same thing, the bandwidth and the variability at nodes. You now have to read 4 things from a graph, but we've tested this against a set of existing graph representations, and while accuracy is about the same as text, it's the fastest of all the representations we've tested so far. So our claim that these are quick things to understand is starting to be substantiated. Osman's rapidly writing this up for his PhD now. Okay, so it's taken, I think, 5 years. Perhaps we can say COVID was in the way, but I don't think. We ploughed on anyway to get to a point where we started off thinking about information theory, that it wasn't great use in visualization, to understanding it might be, to designing some glyphs, and then to testing them globally to try and check that they work in different countries. And we've tested them only in English-speaking countries so far. We do have some interest from China in running some trials there in a non-English-speaking country. Might be a bit tricky, so I'm working on some friends in Japan as well, to try and see if visualization can do what's often claimed, which is sort of bridge across different countries with different languages. So doing this, we can access the uncertainty of these outputs. We can show its use in context. It's usable in these tools. It's not helped hugely yet in comparability, but our next set of work on this might do, because we're moving into some decision-making exercises with different groups. What would I say so far? I still think what Honor O'Neill said, that trustworthiness in data is run by honest representations of the limits of our calculations. We need to put uncertainty more into the public domain, make it an everyday part of conversation about data and data science, if we can. It's a tough call, but it's certainly part of the work that the Winton Institute was doing before David Spiegelhalter retired, was to try and put risk into the public domain in new ways. And we might be able to use this as a representation to do that. So there's a set of different groups we're hoping to work with the next couple of years to look at some new applications of this. Okay, let's see. I have to go I'll go fairly quickly so I stop in time of this. So how do you validate visualization quality? So really, this was very self-interested. How do I help improve my speed of marking using AI and similar tools? Was the question I had. But it turns out that At least initially, it slowed it down a lot because I had to write software, but there you go. But it's starting to ask the question about when can an AI machine of any kind be a trustworthy colleague in doing something? When is it helping you? When is it not helping you? So this is the problem that we had. This is a visualization of a chemical weapon attack on Manchester. This was a project we did with DSTL 6 years ago, I think. They would run thousands of simulation runs, and it's a similar problem. It's an uncertainty communication problem. Which of these plots on the left-hand side are high certainty, high impact areas where they need to send, in every simulation run, where they need to send aid first in the city? So the students had to produce visualizations like this, and we had to mark them, and it's that marking process that I'm hoping to try and automate. This is another more zoomed-in one that I'll use because it's a bit easier to see the data. So the bigger here is the highest impact. The more red it is, the more certain we are. So these are the most certain, highest impact zones in Manchester where you'd want to send aid first if this chemical weapon attack went off. But how do you mark this? Normally you would sit down and look at it and make some judgments as an expert on this. And as you'll see, some of that works sometimes, some of it doesn't. If you want to automate this, it's not going to help us set out learning objectives, but it might help us in setting a bias point, whereas the first class marks. It might help us in removing some prejudice from the system. If you've read Daniel Kahneman's book on noise, you should never trust academic marking. If any students are here, never trust academic marks. Always complain and get us to remark them. Because experts just don't agree by default unless they've got together and talked. If you get them in different rooms, they can be as far apart as 50% of your marks without any malicious intent, just because that's the way it is. And if we can help bring in automatic tools, perhaps we can reduce that. And also, maybe we can have more evidence to think about. So, this is a set of marking criteria. I won't go through all of them, but one of them is color. One of them is Gestalt principles, which is layout, to do with contrast. And one of them is about clarity. One of the things we weren't trying to do was judge anything to do with interaction. It's too hard at the moment for the tools. So we take the student's work, we feed it into the system, and the first thing is a fairly straightforward thing, which I think everyone should do when they don't. This is a simulation of the 3 basic different color vision deficiencies and a black and white print, which everyone should always test things in. And if I can't see your visualization in one of these, then you shouldn't be getting any marks. This one works quite well. Some of the government ones I tested during COVID didn't work at all well. The scales, the color scales, just went from black at each end to white in the middle. Not a good color design. So we run it through that as a basic color test, and that gives me evidence of whether it works or not. So I don't have to say my judgment is. I can just say, look, the simulation based on all our biological knowledge says it doesn't work. There's also a couple of more preference metrics. The color wave metric on the left will give you do people prefer the color set you've used or not? And the metric on the right will say how colorful your image is. And it really does, the ones on the extreme right end are really very colorful images. The ones on the left tend to be very muted, monochrome images. And again, it gives them a feedback on where they are on the scale. The frequency diagram at the bottom is all the other plots the system's ever seen in its running lifetime. Then the one I find really quite useful is the saliency simulation. We tested a bunch of machine learning algorithms for this. They were all very slow and not very good. This is an algorithm by Etienne Koch, which is fast and fairly well experimentally validated as well. Deep gaze to it says there we tried. It really wasn't. That was at the top ranking of all the neural networks in Python. It didn't work very well. But what we're looking for here is, are the things that are data in the image the most salient things? And if they're not, if the title is the most salient thing, or some box on the left with some side information, the most salient thing, there's some feedback to the student that they're not getting the most salient things into the most important bit, which is the data we're trying to get across to the users in the end. You notice the scale at the bottom is perhaps most salient. That's quite common because it's tending to use the same color set as the data. And it might be something you want if you want them to look there first in any case. So, over time, We put this into a system where the student submission would come into a database. It would go, this is 3 of about 8 different algorithms we used. And the algorithms would produce the plots, the graph, and spit them out into a PDF file automatically, so that all of the machine evidence was automatically generated. I would then take that and mark it and just add my comments on the side. So the students would get about, for each submission, about a 10-page feedback on their work, combining my comments, referencing the evidence from the machine systems where it was relevant. I'll say a little bit about this. The areas where it worked best were use of visual channels around using shape and brightness. The saliency helped pick up that. Again, saliency and something called the edge congestion metric worked quite well for Gestalt, which is your ability to pick up patterns in data. The color ones were the most useful by far. And language, actually, when people had written teeny tiny text, it actually showed up as an edge congestion, really dense area. So you could actually pick that up even though it wasn't judging the text content, you could pick up lots of dense text in this as well. And to look at the marks over the years, on the right, so the first year, 2018, 19, 20, and 21. The first 3 years, the marks stayed roughly around the same average as the student count went up from 20 to 77. We got good feedback from the students because it made them think about the visualizations. So it was a thinking tool rather than a marking tool. At the bottom, in this last year, we gave them the opportunity to get formative feedback from the system. So in the last year, halfway through, they could send in their draft visualizations, we'd run it through the system, and only give them the machine feedback. You'll see there's 3 little dits at the left. They all failed the assignment. None of the people who failed the assignment had asked for the machine feedback. Now, that might or might not be causal, but it was an interesting thing to observe. You also see the mean went down. We dropped our standards to pull in a lot of students that year. I suspect that was really behind that. We were very open with the students. We told them we were doing this. We gave them the feedback. We were quite very rigorous on testing it. I tested it on about 100 non-assessed pieces of work too. Does it meet a need and provide a value? I think the answer to that is for me, yes. One thing it did do over the 4 years, and it's quite unusual to do the same assignment for 4 years to be able to do this, is that my marking of color increasingly correlated with the machine's judgments of their color use. So it didn't necessarily change the marks, but it changed me as a marker to give me more evidence base. I learned things from machine feedback too. Some of the real challenges of working in education with AI. There's this terrible thing the EU did, which we're not in the EU, so it may not apply to us, called the EU AI regulatory framework, which is proving, I think, impossible to implement. But in it, they're going to outlaw the use of machine marking, I think, effectively, or actually, they'll be regulated as high risk, and you'll have to do an awful lot of work if you want to get systems approved for use in the EU. So we will see if that, I hope that doesn't get adopted in UK law. There's other issues on ethics and privacy. The small cohorts here, the most was 90. We have to gain permission to use the data, and it tends to be all the best students that give us permission to use the more detailed data. So there's a bias in what we see, which is tends to be the more proficient students. But I felt over time it was useful for me. Feedback from the students was that they really liked it, at least as a thinking tool and as an evidence tool. So I think it contributed to student learning. Was it expensive? For the first 2 years, it was vastly expensive. I thought it would speed up my marking. I spent more time coding than anything. By the 3rd and 4th year, it was starting to pay back, giving marking and evidence to speed up things. And it gave us a way to think about what are human and machine strengths in quite some detail. There's a paper around from Computer Graphics and Visual Computing 2021. They were kind enough to give it the Best Paper Award that year. And if you want to test out some of the algorithms, there's the Alto Interface Metrics website, which does some of them on any image you send in Finland. Okay, how many minutes have I got left? 5, excellent. So that's how do you come up with new approaches to visualization? How do you assess visualizations? How can you create effective data visualizations? And this is probably the most informal bit of the whole presentation. The same example we were just talking about back in 5 or 6 years ago, working with DSTL, just after the Salisbury incident, they were wanting to look at this problem of conveying information to police commanders in the field with uncertainty and impact attached to it. I won't say too much about that one, but we produced an 80-page report. There's a workshop of about 30 of us on all the different ways you could possibly convey uncertainty and impact of a weapon attack on a city for DSTL. This was hosted by the Knowledge Transfer Network, and as was then Public Health England. From that, they then ran a second workshop a couple of years later, this time for the British Army. So we were working directly with captains of the British Army about a weapon attack on a port where we were notionally delivering humanitarian aid, and we knew a weapon strike was coming in the next few days. And there were a set of simulations of the effect of that based on the weather, and the commanders had to decide at what point to evacuate the port. And again, it was about communicating uncertainty. And we came up with this 4-panel plot, which was partly based on the military doctrine. So a request coming in, we define the scenario and the limitations of it. We summarize very concisely the best choices for the commanders. And then, unusually, the captains said they thought they could deal with distribution plots and uncertainties. So these plots are the number of simulations and the number of deaths predicted by each of the simulations on each day. So you'll see the most likely on day 1 is 18 deaths if you evacuate then, day 2, 54, day 3, 38. But the worst case, much worse on day 2, and they're trying to usually minimize the worst case, nearly 300 deaths if they're to evacuate on day 2. So that conveyance of uncertainty, mostly, the military will say they can't cope with it, but we had a set of captains who thought they could explain what this meant to their commanders, so we put it in this time. So this 4-panel plot, request, summary, some plot of uncertainty or other graphics, and some extra details came out of that particular week's meeting. Rolling on to COVID, we then took that, and I was working with a Juniper consortium within the VChems framework. This is a group of 20 or 30 mathematicians modelling the impact of COVID on individual universities. This is Newcastle, we did Warwick, and Bristol, and a couple of others, to come up with guidelines that then went out to all the command teams in the universities across the country of what should they do. And basically, the government was desperate to keep in-person teaching going. All the simulations said you should be online first and in person only when you absolutely had to. And again, we went for this kind of, I won't go through this in detail, we went through this 4-panel plot. We had about 10 of these with different scenarios. This was about how many students you could fit into a lecture theatre and how many infections would come out of that lecture theatre, depending on whether you were talking as a single lecturer, or whether it was a seminar with everyone in the room talking. And from this, we came up with things like the best case in a 164 seat lecture theatre, you just fit 16 students in it. So there's obviously some big choices to be made at universities. So this pack of slides went out, and then they've taken this 4-panel format and reused it a number of times in various modelling groups that they've done. I didn't, but the lead mathematician won an OBE for parts of the work they were doing in this. In fact, 2 of them did, I think. So that's decision-making and representing information to decision-makers. Then there's a question about the public. Some of the hardest maths I've ever seen is in cosmology. And this was Carlos Frank at Durham, who models the creation of the universe from Big Bang right up to the future, using huge supercomputers. But they don't present that to the public. They present beautiful visualizations, and these are top galaxies measured by the Hubble Space Telescope. At the bottom, they're dark matter simulations of how the universe should have evolved under different models of dark matter. The right's one that failed, the left is one that matches what we see today. We presented these at the Royal Society in 5-minute movies, and they're very good at engaging the public, from which I learnt if you want to engage the public, you don't present math to them, present 3D things to them that engage them in something they want to know about. So we've done that in a couple of ways with urban data. This is the terrascope. It was a 1 trillion pixel image we produced of Newcastle. It's equivalent to 500,000 laptop screens, if you wanted to put it on the laptops. There were 2 points to this. One was to see if we could do it. One was to see what would graphics look like 20 years in the future. And it was the first time anyone had used 1,000 GPUs on the Azure cloud. So there's a few interesting things behind that, technically. We also showed it on a whole range of displays. The good thing about having very large images is that they will zoom in and out quickly on whether you've got a large projector screen, a small mobile phone, or your gym cycling machine. We then built this Living Cities film, short film about pollution in Newcastle. What am I doing on time? Okay. And this was conveying what happened if you turn off the traffic in a city centre. So we were quite lucky. During one day there was a march, the whole city centre was closed, and you could see the air quality dropping, the pollution in the air dropping to almost zero, and then coming back as soon as the traffic came back. We produced this film starting from outer space, going down into Earth, showing the city centre and the pollution levels in the city centre. And we thought we were just producing data and just showing people data. But we took it out to various public meetings and showed it around the university, and people got very engaged in trying to understand more about this. I think partly because they could see the city in 3D, partly because they could read the data and see how bad it was usually. And we had a number of people getting very emotional about that, and a number of people trying to think about ways they could not come into the city to reduce the pollution even on normal days. So it's quite an effective, informally effective film. So we're now trying to do some very similar things here in London. So thank you to all these people who've worked on this. Lucy, Osman, Al-Jahara, who's not here, working on rail data, Mike, Steve Downston, Mark Turner, and all these people who've put the effort into the technical side of this, and then collaborators who've done some of the work on the experiments, Arzu in Switzerland, particularly Andrew Woods and Susanna Soon in Australia. And for correcting my statistics, David Firth, who's now president of the Royal Society for Statistics. It's funded by EPSRC, Turing Institute, and UKRI. And on the left is an informal thing we did last year, this time last year, showing the decline of COVID in London as the last big infection wave dropped off. Okay, thank you very much, and any questions?
We have time for a few questions. We also have a lot of time afterwards for discussions less formal. Yeah, David.
So this may be a little specific, but I'm just curious how the saliency map, I know that's part of the automated grading
Sure.
you're using. So I'm a little familiar with those tools, and
Excellent.
it was my impression that you need like a classification outcome, and the saliency is going to tell you what parts of the image are driving that particular classification or something. But I wasn't sure how that would apply here, because this isn't really a classification problem, or at least not obviously. So maybe just a few more details on like what's driving the saliency outcomes.
I think, how did we use it, I think?
Yeah, so like the model itself, you said it's a pre-trained model, right?
It's not pre-trained. I don't think Etienne Koch is an algorithm rather than training. But yeah, the deep gaze one is training, which wasn't very good, as it turned out. So it's a model which will predict what will draw your attention in an image. And so we're interested in marking a visualization, which is the context, what things in the image are going to draw people's attention first. So if it is the page number at the bottom, that's probably not a good thing. Whereas if it's the key data that they're trying to get across, that probably is a good thing. So in trying to give us some evidence that the design might work in real life.
Sorry, I'm still not clear what the label is in the training problem. I think that's my...
In the training problem.
So when you're training the model?
The Etienne Koch one isn't trained, I don't think it's tested. But in the deep gaze one, they were using eye gaze data.
Okay.
So they were just taking loads of eye gaze stuff and training it to predict where the eye gaze was. But it turned out, as with many machine learning things, that wasn't as good as an existing faster algorithm. But it was one of the best. If you look on there's a a league table of about 100 different trained algorithms, out there. But all of the algorithms we used went back to some biological data sets that people had tested with real people somewhere. Yeah, they weren't just made up ones. Salience is interesting. Gestalt will be even more interesting. Can you extract pattern? But no one's got a good Gestalt algorithm, I don't think. We've got a student looking at it now, but we haven't found one.
Thank you for the presentation. I was wondering if you have any insights in your research or elsewhere about the same sort of questions around trust and uncertainty for other data modalities. So I'm thinking text in particular, summarizing text or communicating text in a visual form, graphs. So you've shown numerical data, you've shown maps. Anything more text-based?
Text.
It's okay to just say no.
No, there's a confidential project, but I'm trying to remember what I'm allowed to say about it. I think I can say a bit about it. So text itself, it's interesting because I'm not normally interested in text at all, but it is an entirely visual thing. So you don't text, well, it's not audio, assuming you're reading it. So it is visual. So a security agency were automatically screening incoming text from around the world for saliency in a security context. They wanted us to be able to highlight text that was sensitive in some sense, with some kind of visual form. So we did propose some things that might stand out for them. But their problem wasn't actually that. It was that, as with many machine learning things, the model wasn't reliable enough. It was doing all sorts of stuff. So I think the challenge if that is often the model, not the visualization. If you're saying, what would I do in uncertainty in text, we had some things we suggested to them that you could do. The CIA study said that if you're using text, don't write numbers. Put a word form. People understand word forms much more. 64% is less comprehensible than a slight security risk or something. So that kind of thing. That's an ancient study. There's a really nice study by Chatai in Warwick, just recently on this as well. Text versus image. Yeah, it's an interesting trade-off. So all visualizations tend to have text in somewhere for a label or a description until you've trained people on them anyway. So there's always text there, and I'm quite interested in how much text should there be versus how much image should there be. But as soon as you put text in, you have it stops working in Japan or China or, well, even Germany. Well, actually, not everyone in Germany speaks English, but yeah, you know what I mean. It has less globally. Yeah, it's a tricky one. Text uncertainty, the humanities people will be more talking about your fading pages in your library over time, going moldy and decaying kind of thing, which is possibly an axis you could use. Yeah.
Yeah, so I have a question about cognitive biases. So when you try to visualize risk, we know that if you frame different things in a different way, people react differently. I wonder whether, so in the example that you had of the death, if you give a certainty of death over a percentage of saving people, that will change the outcome completely, right? It's framing. So I wondered whether, yeah, it's part of...
That's a good question. So yes and no. So the no bit first. In most of what we do, we're not in the slightest bit interested in cognitive biases. We're trying to come in beneath that to basic perceptual mechanisms. So we're using the study of first layer perception, really, not cognition, to try and make sure that we can, at some level, ensure everybody sees the same thing. So shape's quite good for that. There are issues with visual acuity, which affect it, but shape's usually quite good for that. In the cognitive bias thing, it's an interesting one because it's well known that certainty, if you talk in a positive way about certainty, people are much more engaging with it. But if you go and talk to a mathematician about certainty, they don't want anything to do with it because that's not what they're calculating. and I haven't really got to the bottom of a discussion with enough mathematicians yet about what they think with that. But I suspect that's different to the public, who would much prefer to know. The people who've solved it at the Met Office, so Met Office in their daily forecasts say 64% chance of rain. People pretty much seem to understand what that means. So there is one example of uncertainty communication that works. I don't think there's a bias in that one. But yeah, but there's a framing problem with
bringing an umbrella is different from the number of people dead, right? So when you have this sort of decision making, and
but it's a similar
this panel there.
question, because it's like 64% chance of 100 people being dead. Yeah. And for military commanders, they're probably less biased by the number of people being dead.
They're more sensitized.
Yeah, but you're right. It's there's a lot of biases. There's a lot of preferences as well, and we try and ignore those.
No, but when you do in support of decision making, you have to consider these things, right? It doesn't. It's not about perception level anymore. Because
then you have to characterize your audience. Yeah, better. Yes, exactly right. Yeah, you do. For military commanders, one thing. For primary school children, completely different thing. Yeah, we do. But we're trying to do more universal things first. Yeah, but it's always there.
Any other question?
Not for anyone?
Look.
Thank you. Thank you for the talk.
Welcome.
You spend a lot of time doing the visualization instead of marking. That's probably because it's more exciting to do the visualization.
You want more marking? Okay, sorry.
That's the side comment. At the beginning, you said there's not enough science, enough engineering for visualization.
Yes.
So at which point do we have enough science and engineering? And do you think you are, with the type of work you've done, you are above threshold? By that meaning, this is really a rigorous scientific and engineering
approach. As a field?
Yeah.
I think there's
No, because I'd like to understand. I'm really trying to understand,
I understand
what is in there.
I understand what you mean. So I should explain some of my own biases, perhaps, to help, and then I'll perhaps try and answer it. So I am, by training, a computer scientist and applied physicist, so I've come out of, in some sense, hard sciences and maths. And a lot of more modern visualization work has come in a much more, has been influenced more by social sciences, where they're trying to address very complex, unsolvable by science methods questions, and have ended up with methods that are quite widely used that do things like ask preference rather than demonstrate evidence that things work across people. My observation, I've been working with psychologists since 2000 and before, 1995, I think. Really hard-nosed experimental psychologists, they're more rigorous than any other scientists I've ever worked with. There is a huge amount of science evidence in psychology about human vision and what works and what doesn't work. Almost none of it has made it into the visualization literature. Very tiny amounts. And it's often been distorted as well. So I think there's a lot of opportunity in that to bring in more evidence from psychology. Steve Franconeri's paper last year, one of the first ones to start to do that, and that was just last year. So I think that's a huge, if you want to, what Robert Casaro was worried about was Tableau and Power BI are just going to collapse because there is no underpinning evidence that they work. It's just, there's evidence from experience, which is of course a thing, but there's still no large amounts of underpinning science that they work. So his argument is we need more, and I think he's entirely right. So there's a few of us around the world trying to address that particular problem.
And how big is that number of researchers compared to the others? Is it a
How many do I know?
Significant chunk of the community?
Not significant enough, no. I think there's a few, but not. Just judging from the response to Min Chen's work from the American visualization community, they don't understand why he's trying to do this. And nor did I for a few years, to be fair. But now you can tweet out, okay, we need to be able to predict what works. We need to be able to demonstrate with evidence that it works. Yeah. There's 5, 6, 7, I could point to 5, 6 or 7 groups beginning to do it. But even in the UK, the groups, I don't want to dismiss them, but there's groups like Edinburgh, very not science-driven, very design and preference-driven, which is fine, but will probably not replicate globally when they test it. You know there's a replication crisis in science anyway. But, yeah.
I'm satisfied with the answer, Elena.
Very good. So can I just make a counter-argument?
Do what?
A counter-argument. So you're saying, well, there's lots of hard science from psychology and it has never made it there, so we actually have no idea if it works or not. But on the other hand, you could argue that if you introduce a new technology to people, people will work with it. Right? So we search information in a very different way because Google has trained us to do that. We know what works and what doesn't in ChatGPT, so we're training ourselves to ask questions in this way. So there is for me at least, speaking as a designer of systems, there is a two-way relationship between the system that you give to people based on certain assumptions, science, empirical evidence, whatever, and what people make with it. So how much of how we use charts in Excel and in Tableau has changed what you thought you knew about data visualization?
Oh, that's a different question. Let me go back to what you said before that. Let me find a good way to say this. There is so much evidence in vision science that is not used, that should be used, that it is a travesty. The whole of computer science in visualization is largely ignoring it, and it is really sad, because as soon as you start to look for evidence, it's there. And to give you someone who was giving a talk 2 weeks ago, a conference I ran in America, was the head of vision science at Apple. They have a scientific model now of how you look at their displays. They can predict in a moving image what you will see, and that's based on all of this evidence. So he's doing it. He used to run the Journal of Vision, so he should be. Meta have got someone who's trying to do something similar, so they're trying to work out the science bit. It's different from design. Design's at a different level of, a different level in the process, I would say. But yeah, it really is a travesty how much computer science is ignoring existing science on what you see on displays, or anything, in fact. It's really rather sad. Because if you go over to psychology, it makes a laughingstock of most visualization people, because they go, well, we knew that 50 years ago. What are you doing that for? There's just heaps of experiments on things like drawing lines, for example, and perception of lines. There's a paper I reviewed last week, and I could point to a paper in psychology 30 years ago which told them the answer. It's not always like that, but it's quite sad to see as a scientist. Not to say that there aren't good things in design, and there are things in design that science can't do, because you have to have designers to think of creative ways to use technology. And don't get me on ChatGPT, and it's many failings, including not knowing who I am.
Okay, yeah, getting into the deep questions. Okay, I think that the truth is somewhere in the middle, so we shouldn't ignore what is known, but we should also try to change perceptions. Okay, so I think it's a good point to stop the formal part of the seminar, and then we will still be here. Around you will be here for a few minutes.
Oh, sure.
So you can ask more questions if you can. Thank you again.
Thank you.